Thank you everyone for attending today. I'm Chip Fairchild, the 50th president of the Caltech Associates. We are a group that has proudly supported Caltech since 1926. During that time, Caltech has brought transformative discoveries and technologies to the world. Our curiosity about nature and the universe itself has led to the invention of the Richter scale, the detection of gravitational waves, the understanding of life on the molecular level, and truly countless other discoveries from fearless research. Annual Associates membership empowers Caltech scientists and engineers to pursue these bold, risky ideas. Earlier this year, as Caltech researchers shifted their focus, resources, and tools to address the COVID-19 crisis, the kind of financial resources the Associates provides has never been more important. We offer a vibrant community of alumni, Caltech parents, and lifelong learners who get to know the scientists and engineers behind the breakthrough discoveries, as well as the science itself, almost in real time. More information can be found at associates.caltech.edu. It is now my privilege to welcome Tracy Fu, the new chair of the Associates East Coast Committee, who follows in the very big shoes that Caltech trustee and alumnus Phil Netchus previously wore as chair. As some of you know, Phil played an instrumental role in bringing the Associates to New York. Tracy is a Caltech alumnus, and together with his wife, Sharon Wee, have been longtime members and supporters of the Associates. Tracy?
Thank you, Chip, for your kind introduction and for your leadership as Associates President. So we originally scheduled this to be a live event in New York City, but like everything else these days, we've gone virtual. On the bright side, we typically have 40 or 50 attendees for an event like this. Today, we brought, 227, making this the largest East Coast Associates event ever. It just took a global pandemic to get here. I also want to offer a big thank you to Caltech trustee and associate Ben Rosen for recommending Jess as our speaker and spearheading this program. A quick introduction on our speaker, Jess Adkins. Jess is the Smits Family Professor of Geochemistry and Global Environmental Science. Jess did his undergraduate work at Haverford and his PhD in Chemical Oceanography, Paleoclimatology, and Geochemistry from MIT. He worked as a postdoctoral scholar at the Lamont Doherty Earth Observatory and then at the University of Minnesota. Jess joined the Caltech faculty in 2000. He's also an associated faculty member for the Ronald and Maxine Lind Center for Global Environmental Science, which brings together scientists from a broad range of disciplines to generate a comprehensive understanding of our global environment. His current research in chemical oceanography centers on the geochemical investigation of past climates. Something you may not know about Jess is that his grandfather was an associate, and Jess has memories of being brought to many events at the Athenaeum as a youth. And even after attending all these events, he's still with us today. Jess, are you ready to begin?
Thank you so much, Tracy, for that kind introduction. That's very nice of you. I do want to say thank you to Ben Rosen for kind of kicking my butt to come and do this talk. I tend to have a back and forth with the audience when I give talks, and so this is truly a bizarre experience. I would be happy to have Ben yelling at me right now to go faster or stay longer on a slide. Only we could do such stuff together. This is a talk that is going to go back and forth between science and engineering. The possible solutions to pulling CO2 out of the atmosphere that my group has come up with really has come out of doing basic research and basic science. And it's been a really fun journey with my good friend Will Burleson, who I think you can see here with my cursor going back and forth. He's my long-term collaborator at USC. We've had the privilege of 3 really terrific students working with us, Adam, John, and Sitcha. Sitcha is with us here today, helping out with the questions. Another title you might give to this is how antacid might store CO2 in the ocean. We're going to be thinking about giving Tums to the ocean chiefly because this is the way the ocean actually solves its CO2 problems, and we'll be going through that as we go along. I would be quite remiss to not thank the really broad-based support that we've had financially and emotionally for doing this work. The Grantham Foundation has been instrumental, Jeremy Grantham's family foundation, in giving us the funds to really push forward on our ideas, the ones that works and the ones that haven't worked. I'll show you some about that as we go along. In addition, we've had generous funding from the Ron and Maxine Lind Center, from National Science Foundation, and especially from Linda and Stuart Resnick via the Resnick Sustainability Institute, who I think many of you know, gave very generously to Caltech recently to help us go after just these kinds of problems that I'm going to talk about here today. The Change Happens Foundation and Kairos Ventures have also been instrumental in helping us move forward. Okay, so this is what I think how many of you enter into this question of global warming and climate change is that it's getting warmer. And so what we have here is 1880 up through just very recently to 2020, global mean temperature as compiled by NASA Goddard Institute for Space Studies. This is right here, I would say here in Manhattan. I'm actually sitting in Altadena, but for those of you that are there in Manhattan, this is just south of Columbia on the Upper West Side. And it's the same place where Jim Hansen had most of his career. They do a terrific job of compiling a global data set and putting it together to see the temperature rise since the 1880s, including historical data, and then doing a nice job of integrating vast data sets as we come in close to today. I'm going to show you here just in a second a time period running from 1960 up to today, but instead of temperature, it is atmospheric CO2. And this is the very famous Keeling curve. Actually, Charles Keeling, who made this curve and started it many years ago, he was a postdoc at Caltech when he first had the idea to try to pull this off. So here we are in 1960 to 2020. And just direct measurements in Hawaii of the atmospheric concentration of CO2 in parts per million. So 320 parts per million is actually a trace gas in the atmosphere. And we can see the seasonal cycle very beautifully here, this red line going up and down, and then a running mean is the black line. And there are all sorts of interesting wiggles in here of slight pauses and slight increases, but unequivocally we've seen CO2 rise quite dramatically, and it's continuing to go up. I think it's useful to put that into historical context. And so here now, instead of just the last few decades along the x-axis, is 10,000 years. So here's the year 0 AD. Over here on the right, we have today. And this is 8,000 BC all the way over here on the left. And we know the atmospheric CO2 concentration because we have ice core data. That's here in blue. The green here is this fern. And then some of the data that I just showed you, the direct measurements are here in red. And I think one of the hardest things to do in the earth sciences, at least, is get your head around the time scale. So I added a few clues in here. First, human agriculture is here at the beginning of this period we call the Holocene. This is kind of a pandemic themed talk. And so here is the plague of Athens. This is Periclean Athens in the 5th century BC when all the beautiful plays were written. History of the Peloponnesian War was written. CO2 is still well below 300. Here's the Black Death, right in the Middle Ages. CO2 has not gone up very much at all. And of course, here we sit today at COVID-19, off the chart for this particular graph, right? I had to point up and above it. So indeed, we're conducting an experiment of really kind of amazing magnitude, but I want to give you one more bit of historical perspective. Now I'm really noodling with this x-axis, mostly because I flipped directions. So that's just so that you're confused. Here is today over here on the left, 0, and this goes back now hundreds of thousands of years, almost a million years, 800,000 years. And in red is a proxy for the temperature over Antarctica. And these warm periods are interglacials. Here's one, here's another, here's another. And these cold periods are glacials. And you can see that you tend to gradually cool, whoops, and rapidly warm. And going hand in hand with that is atmospheric CO2. This is measured directly as trapped in the bubbles or as a clathrate in the ice itself. And as CO2 goes down, temperature goes down, and the abrupt jumps are importantly correlated with CO2. If I put that same data that we were just looking at on this graph, here it is. It really does come up to just about the tip, maybe a little bit over the tip of this arrow right now. And I couldn't draw an arrow thin enough to be able to represent the time. This experiment that we're conducting of adding CO2 to the atmosphere is really unprecedented in magnitude and rate over the last million years and for many million years. But before then, it's very much an experiment. We don't know how it's going to turn out, but there is no doubt that we are conducting it. Okay, well, we don't tend to focus on average climates and these sort of long timescales. For instance, a couple weeks ago, it was 116 degrees Fahrenheit in my backyard. So we all sat out there in little towels pretending it was a sauna. It was really pretty incredible. Here it is just a few days ago, north of Los Angeles. This is the Bobcat fire. Once it's gone up and over the San Gabriels, for those of you who know about the geography of Los Angeles, this actually, we suffered from the smoke of this in my house for about 10 days, just after that massive heat wave, or at the beginning of that massive heat wave. And if that wasn't bad enough, just a few days ago, I was woken in midnight to an earthquake in Whittier Narrows. It was only 4.7, so it sort of shook the doors a little bit. But it was, I looked over at my wife, Tammy, and said, really? Come on, that's just not fair. Pandemic, racial strife, heat waves, fires, and now they're going to throw earthquake at us as well. Of course, I don't think the earthquake is related to the CO2 and the temperature change. It just felt like piling on. So I thought I would complain to you for a second. Okay, so we don't really experience the mean climate all that easily, but we do see these climate extremes very sharply. And so I thought we might take just a brief second to try to think about climate extremes and how to usefully relate those mean longer term changes in CO2 and mean temperature to things like hurricane frequency or more frequent fires. And so here is an idealized version, but you will look at real data in a second, an idealized version of the histogram or the distribution of temperatures over the course of a year. And of course, there's a mean to this, and there's a spread called the standard deviation or the variance. This is the classic Gaussian or the classic bell curve that represents a temperature distribution over the year. Here's the average temperature of the year, warmer to the right, colder to the left. And so extremely hot events sit out here at this tail where 1% or less of the total number of measurements of temperature actually sit. And what happens if we warm the mean climate a little bit, but don't change the variability of climate at all, don't change the spread in this Gaussian, but just push it off to the right? I think you can see here, if we keep our definition of hot events constant, there are many, many more extremely hot days. I think this is a good way to think about the relationship between the mean changes in climate and this interesting, and sometimes frustrating debate that you hear people go back and forth about. It was just in the news in the last week or so, that any one particular fire or any one particular hurricane, of course, cannot be exactly attributed to climate change. But that they're happening more frequently is absolutely a function of the shifting climate. And I think it's relatively easy to see here. Of course, we'd like to look at real data. So here's what actually happened since 1950. This is that same data from the folks in Manhattan from NASA Goddard. And the different colors now are different decades from the 50s up through the early aughts. And we can see this black line here barely underneath. That's just a regular old Gaussian curve like I was showing you before. And the 50s, 60s, and 70s basically lie on this Gaussian curve. But as we move into the 80s, 90s, and 2000s, we finally start to be able to see the shift in the mean, as well as an actual change in the spread. It's a little bit hard to see, but this first arrow that's going back and forth between the shoulders of the 50s is a little bit longer than the second arrow that's going back and forth between the 2000s. But of course, if we put in our vertical line now for extreme events, for really hot days, or we could think about this as more frequent hurricanes or fires as well, in the 50s, there were very few that sat up here at just under 3 degrees. But now there are a massive number. There's a very large number of them that sit above what we would define as a super hot day. And so that exact same principle of just shifting the mean is at work in the real data, and it also includes a slight increase in the variability itself. Okay, so CO2 has gone up, temperatures have gone up, extreme events have increased. Why? What's going on here? Let's see. I think everyone probably knows this answer, but it's always useful to actually look at data. Here are CO2 emissions by type. Here is a rate in gigatons per year, where a gigaton is 10 to the 15th grams per year, going all the way back to 1800 up to 2010, 2011 or so. I think this data set that I got off, that I downloaded from the web and replotted ended about then. And then this one down below, we'll look at in just a second, is the sum of all of these that are up above. I think this is a totally cool plot. I think there's some really neat things in here. Here is the sum. If we look how it's broken down, you can see here this light blue line labeled solids. This is coal. This is English coal, right? And the beginning of the Industrial Revolution. Coal was the total emissions, and so it's lying on top of the line. And it's not until we figure out how to use oil and gas that coal is not the bulk of what's happened. And in fact, it's only surpassed by liquids, which is essentially oil, in the late 20th century. You can see something interesting here, this uptick in coal towards the end. That's China coming online, burning a lot of coal. There are all sorts of cool things in here, right? This is the oil embargo in the 70s. This is stagflation in the early 80s in the Carter presidency. You can really find wiggles that you know about historically in all of these in this line. But of course, what the climate cares about is this one down below. And this line doesn't have little ups and downs and back and forths. It just keeps going up, sometimes faster, sometimes a little slower. But the climate cares about the total amount of CO2, much more so than the rate at which we might be putting CO2 in. The climate cares about this one, and that's really going to matter to us as we move forward here. Okay, so on the next slide, I'm going to show you a very similar sorts of data, starting from about 1980, but trying to go forward in the future. This is the only slide that actually contains some climate model results on it. Everything else that I'm showing you is just about data. First of all, there's actually data on this slide. This is now emissions. Here it's phrased as CO2 rather than as carbon. That's why the scale has changed a little bit from 1980. And then going forward into the future here into 2100. So actual data are these circles that we see here. And then this whole sweep, this big fan of all sorts of crazy colored lines coming out to the right are various scenarios that people have put into climate models for what if we emitted CO2 in a business as usual sort of way. Representative carbon path 8.5, where that's watts per meter squared. Don't worry, that's just IPCC speak. But this is kind of a business as usual path. And then the model result of the temperatures that you see here. If you plug that business as usual into a whole suite of different climate models, they give a range of 3 to 5.5 degrees warmer by 2100. Here's a slightly lower emission scenario, RCP 6, and then some where emissions actually start to turn around. RCP 4.5, and then strongly turn around in 2.6. However, even this one that strongly turns around, the climate is 2 degrees warmer, or somewhere between 1 and 2 degrees warmer. Up close to or beyond dangerous levels of climate change, even though we have drastically changed our addiction to fossil fuels, and in fact, even gone from positive emissions to negative emissions. And that's what the rest of this talk is really about, is this fact that in order to keep from going to very dangerous levels of warming, it's not enough to convert to solar and to wind and renewables. That's what all of these, that's what this line of being lower than business as usual, and these that start to turn around that all do. We actually have to move towards pulling CO2 out of the atmosphere. We must do that lowering of emissions, but it is not going to be enough. Okay, so how to do that? How are we going to come up with any sorts of solutions to this problem? Well, trees do an amazing job of this, right? Photosynthesis runs along, pulling CO2 out of the atmosphere and making wood and leaves and litter and all sorts of great stuff. But trees die, and then termites are very efficient. Microbes are very efficient that live inside the termites, and the CO2 comes right back at us. The mean age of a tree is a few decades. let alone the fact that if we wanted to grow trees and then bury them or somehow not have them respired back to CO2, that would suck up virtually all of the freshwater resources that we have in known aquifers. So if you're going to try to do a carbon sequestration from photosynthesis, you're going to have to do it in the ocean. You're going to have to do it with things that live off salt water and not off fresh water. This is an excellent idea for what to do. Let's take the carbon out of the atmosphere somehow and store it underground, do geologic storage for carbon. I think that this is very much worth working on. There's actually a very large research effort going on from the Department of Energy doing this. And they're going to have to deal with problems of leaks and what about if earthquakes open up your repository. But absolutely, this is worthwhile to keep going. The amazing thing is we know what's going to happen. I don't think you hear this enough in the news and in popular talks and things like that. As geochemists and oceanographers, we absolutely understand ultimately what's going to happen to the CO2. The CO2 that we emit is going to react with calcium carbonate. These are foraminifera shells that are found in ocean sediments. That's chiefly where this reaction is going to happen, to make the harmless bicarbonate ion and calcium. This is taking the acid in CO2 and titrating it with the base of calcium carbonate. The planet has been running this reaction for billions of years. It's one of the main reasons that we're not like Venus, where Venus has become a super greenhouse, lost the triple point of water, inhospitable climate for humans at least to live in. There are lots of interesting comments about microbes in the news recently. The reason you probably don't hear about this very much is that it will take tens of thousands of years. Very fast geologically, right? This is a nice buffering timescale for when volcanoes go off a lot and put a lot of CO2 into the atmosphere, but not so great if we want to save human civilization. So ocean sediments plus human carbon, right? Or limestone plus human carbon, that's the same thing as this calcium carbonate in sediments, gives you slightly saltier water, a reaction that has been going on for billions of years. Okay, we've been working on that reaction in the lab for almost the last 8 years in conjunction with Will Burleson's lab at USC. And we got very lucky a few years ago that we stumbled along a catalyst for it. So this is the rate of reaction on a log scale. So -2 to -7 is 5 orders of magnitude, or a factor of 100,000 across there. On a linear scale, that is the degree of saturation. So more basic or less acidic here, more carbonate ion is closer to equilibrium. Further from equilibrium, if you have more CO2, more acid in the water, you go faster by a lot. And as you come down towards equilibrium, you go slower. However, if you put in this carbonic anhydrase, this really cool looking enzyme, close to equilibrium, we were able to make this reaction go 500 times faster than it does naturally. Well, if you're making the reaction that's going to buffer atmospheric CO2 go 500 times faster, that seems like something that's worth pursuing, maybe even at an engineering scale. And so we got interested in this idea of the accelerated weathering of limestone as a way forward. And there are a few things that you want to try to do straight away. You want to do some back of the envelope calculations. So how does it work if we tried to sequester all 40 gigatons of CO2 or 10 gigatons of carbon, roughly a factor of 4, something like 3.6, that we did last year? What if we tried to take all of that up with our reaction? Well, the first thing is we'd have to go mine a block of limestone 2 miles on each side. All right, that is a very large block of limestone, right? You could make a lot of sculptures out of that. You could make a lot of counter tiles, all the different ways that you use limestone. Chiefly the way that we use limestone in industry is through making of cement. Mining that much limestone is an increase in the cement industry's activity right now is something like 10 to 50 times of what they normally do. If those kinds of numbers scare you, I get it. That is the size of the problem. There's nothing that we're going to do about CO2 that doesn't run into some sort of scale like this. All that is saying we are addicted to fossil fuels, and they've been incredibly useful for us over the Industrial Revolution and making our lives terrific. And now we have to deal, and we have to deal at a very large scale. Okay, so given that we're gonna have to deal at large scales, take that limestone, let's put it into Walmart-sized dissolution factories. This was kind of a fun day on the web, looking up the size of a Walmart superstore. If we ran that reaction at uncatalyzed, we need something like 24,000 factories operating globally, 24/7, 365, in order to process that much limestone being reacted with CO2 to make that salty water and just keep up with what we did last year. Forget about everything that we've done before then. However, if we put our catalyst in, it's 600 factories globally distributed. Currently in the US, there are over 3,000 Walmart superstores on operation right now. And this seemed like, wait a minute, this might be a big new industry, but it is not an unfathomably big new industry. 600 factories anywhere in the world distributed around, that just seemed like something we might be able to do. Okay, so what are we talking about instead of sort of abstract factories? There are basically two considerations. Where are we getting the CO2 and where are we getting the water? So here for the rows are ambient CO2 or very concentrated CO2 sources coming out of smokestacks or flue gas. And then using freshwater or using seawater. Freshwater has this omega much less than 1. Omega is a term that we make up as geochemists so that you don't understand what we're talking about. This is just the saturation state, and it being less than 1 says that in freshwater, limestone already tends to dissolve very easily. In seawater, limestone is about a factor of 3 supersaturated when you start. And so you're gonna, if you add ambient CO2 to seawater, you first have to concentrate it by 4 or 5 times, and you're going to need some sort of catalyst to try to make this reaction go fast enough. However, if you add flue gas to, say, freshwater, couple a power plant like Scattergood with a wastewater treatment plant like Hyperion, both sitting at the end of the runways at LAX right now, you could absolutely take all of the CO2 for the baseload power plant of LA, process it through the wastewater that's moving through Hyperion, and send it out to the ocean. Unfortunately, it works very well in Los Angeles because we harvest fresh water from so many different places. We have a much larger footprint for where we get fresh water than the actual footprint of the city. And this does not scale very well globally, doing it in freshwater. We're going to have to end up in the ocean in all of these cases. The ocean is the largest reservoir by far, by far, by far. It has a massive buffering capacity to be able to deal with this. We'll look at that a little bit. And so flue gas into seawater doesn't need a catalyst. It's concentrated, it's acidic enough CO2 that you could just run with it. And this is where we're headed. Okay, another thing you really have to think about from the very beginning are costs. And so what are we gonna have to do? What kind of things are we gonna have to pay for? Well, we're gonna have to pump water uphill. We're gonna have to blow CO2 around somehow, move it from a smokestack over to a factory nearby. And we're going to have to mine, crush, and transport calcium carbonate. This is far and away the largest component of the price. If we add these all up, they come out at about $60 a ton. But this does not include the cost of the catalyst. The catalyst would be far and away the most expensive part of this, and it became a big part of our research effort, ultimately one that was unsuccessful, as you'll see in a second, to try and get this catalyst to scale. But one of the takeaways here is that it matters a lot whether you bring the limestone in by truck, by rail, or by boat. And this number at $60 a ton is bringing it in by rail. Okay. The other thing you have to think about from the beginning, and I'm not going to spend a ton of time on this slide, is what do the effluents look like? What's going to happen at the end of our outflow pipe where we've mixed CO2, limestone, and water? We have the slightly saltier water coming out. What happens right at the end of that pipe? And there's one version of it in the ocean and another version of it in freshwater. These are my favorite sorts of plots on the ocean side over here. I'm not going to go into it in any great detail, even though I'd be happy to spend the next hour talking about it. But it essentially says here, let's keep track of how much carbon is in the ocean and keep track of how much base is in the ocean. And when we push CO2 in, no base comes, but a lot of carbon does. And our dissolution reaction comes along this vector, and the net effect is no change in the pH whatsoever. we are not going to change the ocean's pH or carbonate ion, right, or PCO2 by very much at all by putting this CO2 and limestone together in seawater. That is that titration or that buffering effect at work. And that's a huge advantage of what we're up to here, is that from a chemistry point of view, we know we're not going to do any harm. There's something similar in freshwater. Freshwater doesn't have nearly the buffering capacity that seawater does, but just with a factor of 4 or 5 dilution coming out of, say, like a single pass cooling plant in a river in Alabama, we would drop below the USGS definition of hard water and be unregulated for the alkalinity that we're putting in. None of this says anything about the ecological responses to what would happen at our effluent, and that is a very important research project that's in front of us. Okay, so here we have moved to the lab. Let's just see if we can get this going. These are fluidized bed reactors that we have built as little toys, basically, in the lab to begin to explore, could we take this reaction that we're doing very well measuring in controlled environments in gas impermeable bags and start to make something that looks a little bit more industrial. And so what you have here are 2 tubes that have gas coming in the bottom. They have water, in this case seawater, flowing in the side. There's already a bunch of limestone chips inside here, and the fluids are flowing fast enough that they fluidize the solids and make this massively turbulent bubbles everywhere mixing environment, bubbling up to the top here, where as we push water through, it comes out this side. We can measure the chemistry of what's coming in and measure the chemistry of what's going out and see how well are we doing on actually sequestering any of the CO2 that we're bubbling in from the bottom, just as a complete lab experiment. Well, we've taken these things, and Caltech Physical Plant has been very generous with us to let us come to the smokestack at the 10 megawatt power plant that Caltech runs just south of Wilson on San Pasqual. If you're ever driving down past Polytechnic, the school right there, and you hear that sort of low hum in the background, that's the power plant doing its thing. They've let us hook up one of our fluidized beds to the outflow coming out of the stack. Now, we take teeny little sips of it. We're not even close to sequestering all of the carbon put out by a 10 megawatt power plant. Please don't come away with that impression. But we are taking real industrial sources of CO2, flowing them in the bottom and running one of these fluidized bed reactors. And here's some data from an experiment like that on the right. It's the running over the course of a day, flowing water through. Alkalinity is what I'm plotting here on the y-axis. Again, so you don't understand what I'm talking about, just take my word for it at this point. This is a very good measure, in fact, almost a 1-to-1 measure of how well we're doing for storing carbon. And so here's the inflow water where it starts. And as soon as our reaction turns on, we have this massive jump up in the amount of carbon stored in the water. There's some fluctuations based on what's coming out of the stack and how quickly the water is flowing. And after 5 or 6 hours, in one of 2 of these, we kept them the same. And in the other one, we added our catalyst, carbonic anhydrase. And we got about a 20% increase in the rate of carbon storage. We felt that felt pretty good to us. We were thinking that was a good thing. Had one major problem to this experiment. Here, we dissolve the carbonic anhydrase in the incoming water. So that also means it's part of the effluent. And there's just no way this is going to work if you take the most expensive thing by far, the catalyst, and use it as a single pass through this reactor, let alone the potential environmental damage of putting this enzyme in massive quantities out into the ocean. And so we started thinking about how to bind this catalyst to glass beads and retain its activity, but keep it inside the reactor. This seemed like a great idea. It only took us about 1.5 years to figure out how to do that. Other people had some success doing it too, so we were sort of following their recipes. And we got all excited once we had that up and working. That's a big chemical synthesis part. And here again, we have time now in minutes, and now this is a reactor here in the lab rather than one at this Caltech smokestack. And we let it run for 4 or 5 hours with 2 reactors. And then after about 5 hours, we added these beads, these catalyst impregnated glass beads, and ran it for another 5 hours. The squares being the one that got the beads, the circle didn't get the beads. and there was absolutely no difference. And then we said, whoa, okay, maybe there's something wrong. Let's just add some dissolved carbonic anhydrase, not bound to these beads, and the thing jumped up just like it did at the power plant. So Ca seems to require touching the surface of the calcium carbonate somehow. If you sequester it onto the glass beads, its catalytic activity goes away. That really was a bad sign. In fact, it got worse because we started doing science and doing better science about it, right? This is back and forth between the engineering side and the science side. There are these very cool instruments called atomic force microscopes. Here's kind of a schematic of one. You have your solid of calcite, calcium carbonate sitting right here. You have a drop of water, and you have this very, very fine angstrom sort of sharpness tip that is dragged across the surface of the calcite. As the calcite has roughness, the tip goes up and down, and a laser that you're bouncing off the surface of the tip very sensitively detects that. And you collect images like the one we see on the right. This is 10 microns by 10 microns, so that's 1% the width of a millimeter, right? That's what 10 microns is, very, very small area. And we have a 10-minute long experiment here, 0 to 3 to 8 to 10 minutes. We're measuring the shape of the surface. These changes in color are now changes at the nanometer scale, so another factor of 1,000 smaller. We're getting down towards almost bond length scales here. And what we see, this darker is deeper, this lighter is closer up towards us. This is a big step on the surface. And there are these etch pits, these places where the surface is being attacked and dissolving. And if we follow this yellow one, I think you can see that the etch pit is getting bigger and bigger and finally engulfed by this step wave coming back after about 10 minutes. That's dissolution of the surface happening right in front of you. And so we move to doing that same thing in the presence of our catalyst, carbonic anhydrase. Here is the same sort of image, now only over 3 minutes. There's a reference etch pit for you now, very, very small one, because this was not very undersaturated. It was close to that basic side. This small one, as you'll see, this black arrow, the one at the end of the black arrow, really doesn't change size at all. We got just incredibly lucky in this experiment in that we had added carbonic anhydrase and it actually flocculated together like little puffy clouds or cotton balls, and one of them landed on the surface itself. It disrupted our ability to make measurements because now this tip is bouncing over these little cotton balls. It stayed there for a couple of minutes and then moved off. And if you look underneath where it was, it's massively etched. The carbonic anhydrase has to be in touch with the surface in order for it to catalyze the reaction. That is a very big bummer. This was not a good day from the engineering side. It's excellent science, right? It's a nice paper that we were able to write, but it just is a solar plexus shot for using carbonic anhydrase as a way to engineer your way forward on pulling all the CO2 out of the atmosphere by mimicking the natural reaction that the planet's gonna run anyway. The mechanism that is at work here, though, has inspired us to think about other catalysts. However, right, just because we discovered this catalyst, right, that made us kind of focus in this area in here. I've been telling you a story that's largely about what if we used a catalyst to make things go fast, close here to equilibrium. But of course, if we just use a source of CO2 that's already very concentrated, like flue gas, like stuff coming out of smokestacks, there's a 5 order of magnitude increase in the dissolution rate the more acidic you make the water, the more CO2 that you put in there. And so why not think about industrial sources of CO2 that might not need the catalyst? That, after a while of thinking, gets you to cargo ships. You might think that's a little strange, but there's several really interesting things about cargo ships. First of all, they're just cool. It's fun to think about cargo ships. And this is the maw of capitalism at work. It's why cargo ships go everywhere all over the globe, is because this is the basic way that we get goods back and forth from where they're made to where they're going to be consumed. Almost always where they're going to be consumed is right here over the US. That means that the shipping industry accounts for 3% of global emissions, a really very large number. They have 5% CO2 in the flue gas coming out the top of the smokestack as they churn along. They have a vast capacity to carry limestone, and we don't need the catalyst for a ship going at 20 knots over the course of its 2-week period across the Pacific, say. We wouldn't need the catalyst to keep up with that 5% CO2 emission over the course of its trip. Let alone it's seawater. Now we don't really have to go pay for water or find water. The boat's floating it. So it can carry a ton of limestone. It's floating in the seawater and it's producing CO2 at a massive rate. The cargo ship becomes the factory. Okay, so what does a back of the envelope calculation look like for a cargo ship? Here is kind of a schematic of a Panamax looking ship with the beginnings of a reactor drawn in with some inlet ductwork and outlet. I'll show you a better picture of that in a little bit. A shipping container, right, just as a unit of volume to think about, is about 38 cubic meters. And on a Panamax ship, the big ones that do the ocean crossings, there are 10,000 or more of these shipping containers stacked up together. We need 24 of those as an equivalent volume to keep up with the fuel burned, filled with limestone. So on a 2-week trip, plus the size of a reactor, that's about 4% of the total volume on a cargo ship. So the immediate question becomes, of course, can the shipping industry give up 4% of its volume capacity to make itself carbon neutral? They kind of have to, because they are under a order from IMO 2050, to have 50% reduction of their 2008 levels of CO2 emission by 2050. Given that cargo ships last for 20 or 30 years, they need to be building those cargo ships right now. And so the industry is under a lot of pressure to figure out what to do about this, and they don't actually have very many good ideas. Okay, finally, right, the water actually helps partially get solved for us as well, because the 20-knot speed of a ship, that's about 10 meters per second. You can run through the calculation that if you open up a 9-foot by 9-foot hole in the hull of a ship, that's enough water flux to carry all the carbon away. In other words, the ship's motion could be the water pump, unless it sank because you just put a hole in the hull. I was worried about that until our consultants in the shipping industry pointed out this is exactly what ships did before they became diesel ships. When they were steamers, they brought in seawater while they were underway in vast quantities to cool the steam, the steam and have their recycled steam loop when they were running under steam turbines. Okay, so excellent. Cargo ships can carry a lot of the capacity, and they might actually help us solve the pumping problem. If we go look at some statistics, I know a table like this is a terrible thing to put in front of you, so let me just highlight some things. This is 2008 in the Port of LA. All of the shipping containers, these are TEUs, these individual shipping containers, coming to Los Angeles and leaving Los Angeles, both loaded and empty. And so I've circled the empty ones for you here because it's a factor of 20 or more that are leaving LA empty that are coming in. And this, of course, is the global trade imbalance. 28% of all the containers processed by the port in 2018 were empty. 8% or so of those were in imports, and close to 60% of the exports were empty. There you go. There's the global trade imbalance. From a volume point of view, I needed 4% of that in order to have enough limestone and have a reactor. We could, from a volume point of view, it turns out from a weight point of view, it's about something like 12 to 14%. We could install our as yet to be built reactors and not significantly disrupt the business model of the shipping industry. Okay, so we're working towards a proof of concept and a prototype. Here is a storage hopper of calcite that you would have on the ship that brings in kind of like a grain elevator sort of way into a reactor tank. It keeps dumping in the solid. There's a gas manifold here underneath that takes in the flue, so main exhaust, hot exhaust from the engine, flue gas coming back the other way, having been bubbled through first this reactor tank and bubbling out the top, and then inlets for seawater as they come along. We've been making models of this sort of process, and as you might imagine, it matters a lot how small you can make the bubbles and how small you can make the grains of calcium carbonate. So we sit up about here for kind of a regular reactor, which is something like 25% efficiency. But we have all sorts of possibilities that at least are going to get us towards 50 to 70% efficiency. This isn't the active area of research. You turn towards modeling during COVID when you're not allowed in the lab. But this has been very helpful for us to think about how we might design this prototype. Okay, Some of you might recognize this picture. We're coming to the last couple of slides here. This is Beckman Auditorium. This is just, I stole it from Google Maps the other day. So here's the Beckman Auditorium. Here is the lawn where graduation happens at Caltech. Unfortunately, it did not happen out on this lawn this last spring. I certainly hope that doesn't turn out to be true for 2021 as well. This is the gene pool and the Beckman Institute, for those of you who know campus. And then right here, this little innocuous structure is a backup generator, a diesel-powered backup generator for this building right here, for BBE. This is the same sort of engine that it scaled down, same sort of engine that exists on cargo ships. It's a diesel generator that makes electricity rather than just driving a shaft to go turn wheels or turn a propeller. It's a diesel engine that makes electricity to power this building. So here is a picture of the nameplating on the side of this thing. John Onderdonk took this picture for me since he was on campus during COVID and I wasn't. And you can see, here it is. It's a 750 kilowatt rated. That's something like 20 to 100 times smaller than what's on a cargo ship. But it is exactly the same mass fluxes and fluid flows and chemistry that we would do to sequester this, that we would do to sequester on a cargo ship. And so we are headed towards trying to build a prototype here in this parking lot and using some of this lawn right now as we try to bring this out of the lab bench and into something that actually might make a difference. Okay, so that was a lot of information. Let me just take a minute or two, right, to make sure we're on the same page. The Earth's temperature is getting warmer and more variable, and this leads to more frequent extreme events. This is the beginning of the talk. I think this is the kind of thing that you get tossed around in political conversations that people try to eat away at. I want you to just remain focused on the data. It's just unequivocal, these statements. We're getting warmer, it's more variable, and there are more frequent extreme events. And we basically understand why. Rising levels of CO2 are the reason, and we have no good analogs or answers for how that CO2 is going to affect the climate system on these short time scales. However, we know that we have to lower emissions, but at this point, it's not enough. We have to remove CO2 from the atmosphere if we're going to try to keep our climate below unsafe levels. There are lots of really interesting ideas about how to go about doing this. I'm into the idea of just in the same way that burning fossil fuels is extracting organic matter out of rocks faster or letting off more volcanoes, just doing exactly what the planet would do in order to make up for that. And that's weathering of calcium carbonate into ocean water. And again, there'll be no change in ocean pH, and we'll actually be helping somewhat with ocean acidification. Global shipping is about 3% of emissions. It can be made carbon neutral without possibly gratefully disturbing their current business model, with something like $60 a ton of CO2 sequestered, though there's still big uncertainty on that number. And something that I didn't actually mention very much, though, is that you could go beyond just the shipping industry with this. There are purpose-built cargo ships now just carrying limestone with direct air capture devices that are already at work in several different businesses around, could suck CO2 out of the atmosphere anywhere the ship drove, it doesn't matter where you take it out, and put it back into the ocean at scale. This particular approach can scale to solve the whole problem if you couple direct air capture with the cargo ships. Okay, I'm going to take kind of a deep breath and just want to remind you of one thing here in this last slide. It seems like a lot to take this on, right? It feels like, oh my gosh, global scale problem. We're going to have to, like, what I'm hoping to do is enable a global cap and trade program for carbon, or a global carbon tax to actually work, because you have a negative term that actually is big enough. But I want to remind you that we've actually done this kind of thing before in two really good examples. The first is the Clean Air Act. So here's another one of my favorite plots, right? 1850 coming up through now only up to 1990, but instead of CO2 or temperature or hurricanes or something, this is the lead content of corals in Bermuda. There's no lead in the corals before the Industrial Revolution because there's no appreciable amount of lead in seawater. And those of you who know Claire Patterson or knew of Claire Patterson know that this is the kind of thing that he worked on very acutely towards the end of his career. This data actually happens to come from my advisor at MIT, not from Claire's lab. This is Ed Boyle's work. But we can see as the Industrial Revolution was coming on, there's more and more lead accumulating in the reefs in Bermuda, out in the middle of the ocean. In the onset of the American era, the slope really goes up. And in 1971, 1972, with the major passage of the key cornerstones of the Clean Air Act, lead starts coming down. Good policy leads to good results. If you think you understand what's going on, and we didn't totally understand how it is that corals take up lead, but it's quite clear that the lead in the catalytic converters that got banned in order to make our air better, the lead in the gasoline that got banned because of poison catalytic converters, which were put in to make our air better, that lead stopped accumulating in the environment. And the last one is that we've actually done this through economic and market-based means. We instituted a cap and trade system to deal with acid rain in the 90s. So, and again, it was very important that the industry had some possible technical solutions for ways to stop the sulfur emissions to the atmosphere. And so here are the emissions in this red curve from 1990 to 2002. And then when they were putting together in the Bush era, right, this is all Bush White House, what the projected cost of a government mandated cap and trade program would look like. It was this dashed line. When the program opened, it was this, here are the actual costs. It came out much, much cheaper and drove down emissions. Acid rain stopped accumulating, and the lakes in the Adirondacks, my favorite place on Earth, have recovered since this time and are doing much, much better. We have the capacity to pull off these kinds of things. CO2 is hard. It's at a global scale. It's going to require countries actually talking to each other, but we have done it before and we can do it again. Okay, with that somewhat, I hope, hopeful note, I'm going to turn it back to, I think we have about 5-10 minutes to take some questions. I think we're going to open it back up to Tracy and Sitya helping us out with that.
That's right. Please use the Q&A feature down at the bottom of your screen if you would like to ask a question. Jess, we have our first question from Jeffrey Richardson, and his question is, what is the explanation for the mini ice age in the Middle Ages?
That's a great question. Thank you very much for that, Jeff. There are a few different versions of an answer because I don't think we can tell you the exact levers and cogs of exactly what happened. The first part of the answer is there is interannual and interdecadal climate variability. The Little Ice Age is part of that, just like the medieval warm period before it. And so there's absolutely natural climate change. Everything that I have shown you is very, very far above the threshold for natural climate change being the cause of anything that we're seeing. It's just not really a question in science anymore. It seems to be a question in politics still, but it is not a scientific question. It only is a scientific question for kind of the reason you're maybe asking it, which is, could we learn something about how the climate system works by looking at temperature warmings and temperature drops? That's literally what my lab did every single day until we discovered this catalyst. But using the history of the climate system to understand the internal physics and, is just an absolutely fascinating problem, one I love working on.
Our next question comes from Jason Wen. It says, his question is, CO2 contribution from wildfire and or volcano compare with human emissions? How do they compare?
Yeah, that's also a great question. And in fact, I would very much say it's important to separate out those two, fires versus volcanoes, because fires are burning wood that was fixed out of the atmosphere just a few decades earlier. And so fires are just fast termites, right? So all fires are is a recycling of carbon through photosynthesis and respiration. It just happens to be respiration that's happening in a very combustible, very violent way. Volcanoes are not that. Volcanoes are CO2 coming from deep in the interior of the earth, They are new CO2 to the system, and they absolutely pale in comparison by orders of magnitude compared to human emissions now.
Okay. Thank you for that question. Our next question comes from Alan Lee, and he's asked, his question is, how much CO2 is generated by the process and energy inputs?
Let's see, I think you don't mean like globally, what's the CO2 budget, Alan? I think you mean, what about, we have to make sure we count everything up correctly in our process, right? That we can't just say, hey, look, great, we're dissolving this limestone and sucking CO2 out. How much power did we need to do that, right? So we use 1 cent per kilowatt hour as our metric in that $60 a ton calculation. It was a little note at the bottom of the slide. It was easy to miss, but I think this has been recorded, so you could go back and look at that. So we kept track of what power requirements were required to get us to that $60 a ton number, both in the processing, for process and energy inputs.
Okay, I think we have time for one last question. This will be from Jamie Schwartzman. So when you consider the carbon required to mine the limestone, does it still work out to be a net positive?
Yeah, that's basically the same question that we just got. The short answer is yes, but of course, we would love to have quarries closer to ports than further away. But once you get to, one of the beautiful things about the cargo ship part is that you can bring your limestone in by barge. That is very, very cheap, both in its energy and in its actual dollars. And so it turns you back towards the mining and the crushing. Sitch has actually looked into this. We're trying to come up with a good techno-economic model to have nice answers to these sorts of questions. It's really interesting, the price of limestone in China and the US. Limestone is actually a global commodity. The prices track each other. The price jumps rather sharply as you get smaller and smaller grains, as you might imagine. Big cobbles don't cost very much. That's one of the reasons we pick a 100 micron grain as our reference point, is because that's still very cheap, both in its dollars and in its carbon input. To make much finer dust, we're absolutely gonna have to worry about that. The real techno-economic analysis is a few months in our future.
All right. Well, thank you so much, Jess. That concludes our event. And I hope everyone here is able to join us for our next virtual event about earthquake science. It's on October 22nd. Thanks, everybody.